Assalamualaikum warahmatullahi wabarakatuh. It's a pleasure to meet you again at MA 3051. I am Edy Tri Baskoro from FMIPA ITB. Today's lecture is about how to count trees. Enjoy listening. Well, in this section, we are going to count all label trees on n vertices. Okay? But before we doing that, let's define edge construction here. HE in a graph G is it to be contracted if this edge is deleted from the G and the two end vertices of HE are identified and the resulting graph denoted by G dot E. Okay, so the number of vertices G dot E is equal to the number of vertices of G minus 1 because we identified two vertices in G, and the number of edges of G dot E will be equals to the number of edges of G minus 1 because we contract an HE, and the number of components of G dot E will remain the same with the number of components of G. So, okay, this is the example. If we have a graph G here with 5 vertices and 6 edges, then if we contract an edge BD, then we will have this graph. Yeah. Now, denote by tau G the number of spanning trees of G. And we have the following theorem. For every HE in G, tau G is equal to tau G minus E plus tau G dot E. Okay? So now let's see the proof. We will count the spanning trees of G by considering two cases. First, we count all spanning trees of G which do not contain an HE. So, in this case, each spanning tree of G will correspond to a spanning tree of G minus E, right? Look at this figure. If you have a spanning tree of G which doesn't contain an HE, like in this figure in the left side, then you will have corresponding spanning tree in G minus E, like in the right figure, and vice versa. Yeah. So tau G minus E will be the same as the number of spanning trees of G containing no E. Okay. And then for the second case, we count all the spanning trees of G which do have an HE. So in this case, each spanning tree of G containing an HE, when you remove an HE from the spanning tree, then you will have a spanning tree of G dot E, right? Or vice versa. Or if you start from having a spanning tree in G dot E, then you add an HE to this spanning tree, then you will have a spanning tree of G which containing an HE. Yeah? So in that case, the number of spanning trees of G containing an HE is tau G dot E. Okay? So in that case, we have proven this theorem. This theorem provides a method to count all spanning trees of graph G. However, this is not suitable for large graph since we have to calculate recursively of the tau G here. I give you example. Suppose we want to count all the spanning trees of graph G here. Small graph G with four vertices and 5 edges. Yeah? Then if we use the previous theorem, then we have to divide into two parts. First, yeah, we count the spanning trees which do not contain E. Yeah? So represented in this graph. Yeah? This is G minus E, right? Plus the number of spanning trees in G dot E. You contract an HE, you will have this. Yeah? So that means according to that theorem, yeah, the number of spanning tree of G is equal to the number of spanning tree of this graph plus the number of spanning tree of this graph. Yeah. Now we do the same process for this graph. To count the number of spanning tree of this graph, yeah, we can take this as an HE, yeah, this one. So you will have the number of spanning tree of this graph is the same as the number of spanning tree of this graph plus the number of spanning tree of this graph. And then we also can do the same process for finding the number of spanning tree of this graph, yeah, by splitting into two. Yeah. It's equal to the number of spanning tree of this graph, yeah, by considering this is an HE, yeah, and then you contract here, you will have this graph. Yeah. We do the same process repeatedly until we have the last line here. Every graph now having a single spanning tree. Yeah. So we have altogether 8 spanning trees of graph G. Yeah. So imagine if you have a graph G is very large, yeah, using this theorem will be not so efficient. Okay. Fortunately, Cayley in 1889 discovered a simple formula for tau G if G is complete graph on n vertices. Yeah? We will solve this nice formula and prove it by using the method of Prufer. This is the nice formula found by Cayley. The number of spanning tree of complete graph on n vertices is equal to n to the power of n minus 2. Okay, now let's see the proof. Let the vertex set of Kn be capital N. This is the set of 1 to up to small n. And then note that n to the power of n minus 2 is the number of sequences of length n minus 2 that can be formed from capital N. Right? If each entry in that sequence is a member of capital N, then you will have this number, right? Thus, to prove this theorem, it suffices to establish one-to-one correspondence between the number of spanning trees of Kn and the number of such sequences. This is the illustration. So we have to find one-to-one correspondence between the left side with the right side. What is the left side here? the spanning tree of complete graph on n vertices. And then on the right side is a sequence of length n minus 2 from the capital N. Yeah. Okay. This is the process from left to right. We are given a spanning tree T of Kn, and then we would like to associate this spanning tree with a unique sequence T1, T2 up to Tn minus 2, yeah, with Ti in capital N. And we do this as follows. Consider N, the set of N, as an ordered set. And then let S1 be the first vertex of degree 1 in T. Yeah? T is a spanning tree, right? And the vertex adjacent to S1 is taken as T1. Yeah? And then now delete S1 from T and denote by S2 the first vertex of degree 1 in T minus S1, and take the vertex adjacent to S2 as T2. Yeah? So you have now, in this step, you have a sequence T1, T2. Yeah? Then this operation is repeated until Tn minus 2 has been defined and a tree with just 2 vertices remains. Okay? It can be seen that different spanning tree of Kn determine different sequence. Yeah? So from this process, we have associated a spanning tree of Kn with the unique sequence of T1, T2 up to Tn minus 2. Okay? For example, I give you this illustration. So suppose we are given a spanning tree T of Kn here, and then we find the smallest vertex of degree 1, which is 1 here. So we remove this, and then we write a 3 in our sequence. And then we have the resulted tree here. And then we look for another vertex of degree 1, which is the smallest, which is 2 here. And then we look at the vertex adjacent to it, which is 6. Then we copy 6 here. And we remove 2 from the tree. So we have now the resulted tree is here. Yeah. So we do the process, the same process, until you end up with a tree with 2 vertices. Yeah. Once you have tree with 2 vertices, then stop. Yeah. So we have the sequence with correspond to the given spanning tree here. Next, we consider from right to left. So we are given a sequence of length n minus 2, and then we like to have a spanning tree of Kn which associate with this sequence. For any sequence T1, T2 up to Tn minus 2, there will be a corresponding spanning tree T of Kn. Before we establish the procedure, observe that any vertex V of T will be D minus 1 times in this sequence appears. Yeah? So that means the vertices of degree 1 in T are precisely those that do not appear in the sequence. So now, to construct T from the sequence, proceed as follows. First, let S1 be in the first vertex of N, not in this sequence, and then join S1 to T1. T1 is the first entry in the sequence. Next, let S2 be in the first vertex of capital N minus S1. Yeah. You remove S1 from the set of capital N, which is not in the sequence, then join S2 with T2. Continue in this way until the N2 edges S1 T1, S2 T2 up to Sn minus 2 Tn minus 2 have been determined. Yeah? So you already have N2 edges. Yeah? So in that case, T is now obtained by adding the edge joining the two remaining vertices of N, capital N, minus this set. Yeah? Okay, so this is the procedure to associate a sequence of length n minus 2 with a spanning tree of Kn. This is the example. Let's suppose we have this sequence 3, 6, 3, 5, 7, 7, 6. Yeah? And then you have capital N is in this sequence 1, 2, 3 up to 9. Yeah? Now you look for here the smallest entry which is not in here. So in that case you have 1 here. It's not in this sequence. So you connect 1 and 3 in your graph. So you have an edge 1, 3. So this is S1 and this is T1. Yeah? And then you remove S1 from N. You have this, and you remove T1, which is 3 from the list, yeah? From the sequence. So you have this. And then look for a smallest entry in N, in capital N, which is not in here. So this is 2. So you connect 2 and 6, yeah, become an edge in your graph. Yeah? And then you remove 6 and 2 from the sequences. And then you have this one. Again, you look for a smallest number in here, which is not in here, which is 4. So you connect 3 and 4. Yeah? You have this, and so on, up to the last step. Here you have empty in the first sequence, and then you have 2 numbers in the second sequence. So you stop that by adding these 2 numbers as an edge. So this is 6, 9 as an edge in this graph. So you will have the associated spanning tree of Kn, yeah, for this sequence. Okay, so this is the process to prove the second part of the theorem. Okay, so this is the end of our section, and thank you very much and Assalamualaikum warahmatullahi wabarakatuh.